I'll be introducing your speaker. She's Elizabeth Kennick, and she's the president of Teachers in Space. She joined Teachers in Space as program director in 2011 and became president in 2014. Formerly vice president of client technology at Morgan Stanley, she now splits her time between developing exciting ways to bring space into the classroom and funding space flights for classrooms, experiments, and for teachers. Liz has flown in 4 parabolic microgravity flights. That is awesome. Most recently in 30 Parabola 0G flights as a spacesuit test engineer with Final Frontier Design. Now she wants teachers and students across the world to communicate with Teachers in Space, first educational satellite, Serenity. Liz holds a master's degree in information systems operations analysis, is a certified project management professional, and is the leading Teachers in Space build and deployment of the first orbital satellite, launching with Firefly Aerospace later this year. She's co-founder of NYC Soft Process Improvement Network and teaches systems engineering concepts and process, Arduino and Python programming, data management, critical thinking, decision process, and test design and management. Liz placed 17th among New York State women her age in 2018 CrossFit Open and 387th in the world in 2019. Ladies and gentlemen, I introduce to you Elizabeth Kennick.
Thank you so much. And thanks everybody for joining the call. I'm excited to talk to you about our first orbital satellite, an educational satellite called Serenity, that Teachers in Space will launch with Firefly Aerospace this year. We've been developing standard CubeSat models for classrooms since 2012, when we started with 3D printed 1U, 10 centimeter on a side, CubeSat frames, and Arduino components. We've been flying those on balloons and on the Perlan 2 stratospheric glider since 2015. We flew a 2U version with Blue Origin last year, and we are able to do that repeatedly, so we have that standard available. This is the 3U version. This one has solar panels and a radio and an antenna, and it's going into orbit. And so this will be the first one of these satellites, CubeSats, that we work with that we don't get back. Normally we get it back, we pull a data chip and we download the data to a laptop. This one we're going to work with radio communications, and that's what I'm going to talk to you about today, how we're going to do that and how you can do it too. So where do we fly? These are some places that we have flown in the past. Our very first classroom experiments flew to the International Space Station, and those were from contests that we ran in 2012 and 2013. The winning experiments both flew in 2014 when we first began having flights up to, on Cygnus, up to International Space Station, so the beginning of the commercial space resupply missions. Then we began working with some high altitude balloon flyers, and we started some of our own clubs. We have one that we still run in Gloversville, New York, and teachers who came through our program have started some in Kansas. We work with folks in Georgia and in California, and we've had people just get our CubeSats and fly it themselves. So that's an ongoing thing. Then in 2015, we got a sponsorship from the Airbus Perlan project, who were building a world record-setting stratospheric glider. They set many records just a couple years ago, and they helped us run a program where we got 10 of these 1U CubeSats built with experiments designed and built by students. We had a preschool playground from the Oregon Museum of Science and Industry, 3- and 4-year-olds with an experiment on what happens to marshmallows when they go to space and return. Then we had middle schoolers, 6th graders, high schoolers, and even some junior college. So a really fascinating array of experiments. We flew a 2U version with Blue Origin last year. That was a big success. And that one continued an experiment that came out of that Perlan project program. There was a class in Gloversville High School which is the same school that has started and still runs our high altitude balloon program. An 11th grader there wanted to know what would happen if we wrapped a Geiger counter in a new kind of radiation protection and kept another Geiger counter unwrapped. And that experiment has proved easy to do, successful and interesting, and it's been repeated by a number of schools on the balloons, on Perlan. It's what we flew with Blue, and that experiment is going up on this orbital satellite as well. So I'll talk a little bit about how that experiment works and what you can do as a teacher with the data that comes back from it. Okay, so why? Why would we do flight experiments? Teachers in Space, you can tell by our name, our goal, we want to go to space. That's what we want to do. Well, it's been 10 years since we started as an organization. Nobody has given us a flight for teachers yet. We want flights for teachers, but what we can get, what we have been getting for 8 years now, is flights for experiments. And that is pretty darn exciting. So we find that the students and the teachers love building these things, love that they're in charge. They can control it, they can change it. What if I do this? What if I do that? If you break it, it's not that expensive. You can fix it, you can replace it. I was unpacking some the other day to get ready to put this presentation together. My 7-year-old granddaughter came in. What's this? This one isn't working, she says. Let me see, she says. Do you have any tools? And she found that there was, I've just moved, it had come loose and there was a nut missing and a screw missing, and she tightened it up and got the display working again. So excited. I've never seen her so excited. It works. And she did it herself. So this is just an amazing opportunity for teachers and students to build things that they can fly and they get the data back. It's project-based, it's experiential, it's standard. We publish exactly how you build one of these. You can buy it from us, you can build it yourself, and it's going to be the same as what other schools have done. That's where you start. You start with the standard. You can repeat their experiment. You can say, I want to do something different. You can compare it. And there's just so much. The more you do, the more you find that you want to do. And costs are coming way down. We did not think that we would be putting something into orbit, but here we go. So this is where we started. In 2012, we started with these 1U cube-shaped frames. It's a CubeSat. It's a form factor. It doesn't have solar power. It doesn't have any power, but you can put it on a balloon and fly it and bring it back. You can put it inside the glider, fly it and bring it back, and many schools have done that. You can put sensors inside. You can learn what happens to an exposed experiment as it goes up on the balloon and comes back down. What's the impact in the change of temperature, change in oxygen, carbon dioxide? Is it going to freeze? Is it going to frost? Is it going to fog? Will it survive coming down? What kind of data do you get? Can you work with that data? Did you record too much or too little? Do you know how to put headers on it? Do you know how to change it from comma delimited text into fields in a spreadsheet that you can actually work with? So much learning to be done just with the 1U version. 2U version we developed for New Shepard. Now, the thing that's been interesting for us, our goal has always been, how small can we get? The smaller and lighter it is, the less it costs to fly. However, as we work with new vehicle providers, there's another factor to consider, which is what is the size of their payload bay. And in fact, for Blue, one of the new things that they were working on the flight that we flew on was a feather frame from NanoRacks. NanoRacks is a payload integrator. They've flown our experiments when we flew with SpaceX and when we flew with Orbital ATK. They also provided the feather frame for New Shepard, which holds a 2U, right? It packs a bunch of 2Us into a locker. And we said, okay, we can make a 2U version of this. And we put the Geiger experiment in one end. And then in the other end, we built an integration. Blue and NanoRacks were willing to share with us how their power and data from the vehicle are provided to the feather frame. And so we were able to make a USB connection. And instead of having to use batteries, reduces the weight, we were able to plug our CubeSat directly into the vehicle data and power, run it that way, and we got back not only our own data from all the same standard sensors that we fly and the Geiger experiment, we also got the vehicle data. So I found when I go and talk to high schools and I'm working with them on how to use, whether it's Google Sheets or Excel, how to change your comma delimited data into spreadsheets that you can work with, Students love the fact that this is real space data from an actual rocket from a Blue Origin flight. So, you know, there's nothing like giving them something they care about. So this was a successful flight. We can continue to fly with them. And the cost of flying a 2U experiment like this with Blue Origin, just the flight, is only about $8,000. $8,000. I can remember when it cost half that to fly a balloon. Balloon prices have come way down too, but this is the amazing thing. The equipment's getting cheaper, the flights are more available, the flights are cheaper, and now this is something we can actually do. So right after we did that flight with Blue Origin, somebody that I work with called me up and said, hey, did you know there's a new aerospace company in Austin, Texas. This was May of 2019. They're called Firefly, and you have like 3 weeks to get a proposal in. They're going to choose some payloads. You get a free ride. I thought, yeah, you know, I was running a little on that high. If we just had the success with Blue, why not go the next step? Why not try for Orbital? So we applied, and what we thought was, let's just, you know, take a baby step. We'll succeed. We'll go from 2U to 3U because their minimum size is 3U, and we'll just stay attached, right? We don't need to deploy, and maybe we'll take some photos. And of course, they came back to us and said, why don't you deploy? And they talked to us about how much better it would be if we deployed. And then we have a communications expert and licensing expert, Mike Miller, that we work with in Montana, and he said, yeah, you should deploy. You know, and enough people say you should deploy and think, maybe I should deploy. So we worked on it. We worked with others. Our engineer, Joe Luttrell, has been working on this for smaller sized satellites, and we thought, let's figure out how we do it for 3U. Why should we do this? Well, we're expanding those affordable spaceflight opportunities, right? Now classrooms, they can't just build a 1U model, not just fly it on a balloon, not just put it on a suborbital flight. Let's put it into space. Let's talk to it. Let's get data back from it while it's in space, and then let's talk a little bit, if we still have time, about where we go from here. What do we do next? This launch is expected to come in September. Right now, the launch window is between the 14th and the 21st of September. So that's really exciting. In fact, we just had our fit test last week where everybody sent their payloads to Firefly, and Firefly put them all into the components that they're going to fly in, and I'll show you some pictures of that. Send us back the pictures and the results, what worked, what didn't work, did anything get damaged, does anything need to be changed. And we found that our satellite does fit in the bay it's been assigned within the QUADPACK, where 4 of these will go. And so it is expected that it will deploy properly, and the antennae will release, and we'll be able to communicate with it. So pretty darned exciting. You can see in this picture here, there's some solar panels affixed. Those are our very own Teachers in Space solar panels developed by Joe Luttrell, our amazing engineer. And they will keep the battery charged once the satellite has been deployed. So we charge it, we ship it to Firefly, they load it, they launch it, they deploy their QUADPACK, and then the QUADPACK deploys the satellites, and the satellite will switch over to solar power, which will keep that battery charged, and we'll be able to talk to it. We're going to have the same sensors that we always have. We're adding a GPS. We're going to have pressure, temperature, and we've got 2 lightweight radiation dosimeters. So we're doing the two radiation measurement experiment again, and a little Argicam. We're going to get pictures. Okay, who can talk to it? Anybody with a ham with an amateur radio license. Okay, so a little bit about Firefly. And I pulled this straight from their website, and the websites are linked here at the bottom of the slide, firefly.com. We are on the alpha launch because it's the first launch, which is super exciting. We're one of, I think, 7 technical payloads that were selected, and the rest are art and cool things. But we're really, really proud and pleased to be one of the 7 technical payloads. While the company is in Austin, and that's where the testing's been taking place, the launch will occur from Vandenberg Air Force Base in California. And you can see on their website types of future launches that they will offer. 1,000 kilograms delivered to lower Earth orbit, 630 delivered higher up to sun synchronous. The higher you go, theoretically, the longer your satellite stays up. We're going very low, and we don't know that we'll get more than a month out of this satellite. First time for us, first time for Firefly. People who have given us the equations calculate a month. So that's what we're looking at, and we're eager to get the word out. Looks like you're going to have a month from some time. We'll tell you when. Looks like September until maybe at the end of October to talk to the satellite and get data from it. Okay, here are pictures. Never seen before by anybody outside of this group because they just came back to us. And in the middle of the top row, you see the QUADPACK dispenser. Ours is one of 4 payloads, 3 U-sized payloads that fit in there. So this is another great thing about standards. The more we all use the same standard, the more you can switch among vehicles and flight providers. Everybody builds to the same equipment and things become interchangeable, and that really drives down costs, and it means that the experience you get with one flight is going to apply to future flights, and we become able to teach these things and build on them, and so everything starts to happen faster, easier, cheaper, better. In the upper right corner, I put a box around. You see Serenity with the yellow tape measure antenna folded down, sliding into the bay in the QUADPACK. All right, there it is. That's Serenity, sticking up slightly out of the QUADPACK. The QUADPACK will deploy when the Firefly rocket reaches the orbit insert point, so 300 kilometers up. Then Serenity separates from the QUADPACK. There will be a battery voltage and temperature check. The solar charging will begin. There's a check out of that. There's a check out of the sensors. Photography begins. Pictures will be taken. We're trying to get pictures of the Firefly rocket. I hope that that's going to work. And then 30 minutes approximately from when the satellite has deployed into orbit is when the antenna will deploy, when it's nice and clear and not going to bang into anything. And then the communications will begin. Okay, so I hope you can see this. This is a skinny little timeline of what I just said. So running across from the left, it says T0, T0 meaning we're going to start counting from deployment, when the satellite leaves the QUADPACK. Sometime in the first 3 days, so immediately after it leaves, there's going to be the checkouts of the sensor, the charging begins, the solar power. 30 minutes later, the antennae come up, and Serenity enters the first of 4 modes of communications. Mode 1, M1, it's in beaconing mode. It just keeps sending its call sign and its health. So it's just saying its call sign, I'm okay, or my call sign, I'm not okay. And it's going to keep doing that about every 5 minutes until either, and this is the little thing on the downward bracket, what's expected is that we'll hear it and we'll talk to it and we will send from our ground ops the signal that changes it from beaconing mode to mode 2, public mode. And when it's in mode 2, you can talk to it. If for some reason we fail to do that, if anything goes wrong and prevents us from making that change, it will happen automatically at day 3, 72 hours after deployment, whether we've talked to it or not. The satellite will switch from mode 1 beaconing to mode 2 public. And then you can talk to it up until whenever. So that final bracket, worst case scenario, it might only stay up 11 days. We expect it's going to go for 30. Everybody has a story about the satellite that's still up there 2 years later. We can't count on that. We can't count on anything, but our expectation is we're going to get 30 days. So we urge you to talk to it in that first week. Okay, what are we using? We're doing, I think I mentioned COTS, COTS, commercial off the shelf is the concept that we're using. As much as we can, if we're building stuff, we try to build it the same way all the time and to publish how we're building it and to build it to standards. But wherever we can, we're buying stuff that already exists. And in this case, as far as we know, this DORG DRA818U UHF band voice transceiver has never been used in space. So we're going to use it in space. We think we can use it in space. It appears to be space rated. This is what we're going to talk to. I pulled this right from their data sheet, and you can get the data sheet from their website. So if you want the details on this thing, here it is. It's a DORGI, D-O-R-J-I, and the model is DRA818U, and you can pull a lengthy data sheet all about it. This is just a diagram of how logically the communications will work. On the left, Lancaster, Pennsylvania is where Joe lives. He's our command and control. He's in charge. It's his satellite that he built with and for us. And he's going to talk to it using a TCP/IP connection to our ground station, which is at the Cedar Grove ARC, Amateur Radio Club. Rocco Conte is our guy there. He's super excited. He's one of those guys who has a Yagi antenna and likes to track satellites. Now he's going to have a satellite he can actually talk to. So Joe and Rocco together will control the satellite. And when I say control, it doesn't have any propulsion. We're not driving it around. All we're doing is telling it what mode to communicate in. We're going to move it from mode 1 to mode 2. And if we ever need to turn it off or do other things to it, that's what 3 and 4 are for. But primarily, it's going to be in mode 2, public mode, and you can talk to it. As you see the houses on the far right, various amateur radio operators. If you, like Jim Cole, who's on this call, have a ham license and a radio, you can talk to it. If you, like me, do not, then I'm going to tell you how you find somebody to work with so that you can talk to it. It's not encrypted. It's on the amateur band. Anybody with an amateur license can talk to it. Here's how it happens. If you're in the US, go here. Go to ARRL. It's the American Radio Relay League. And when you go to ARRL.org, you're going to get a website that looks like what I took a screenshot of. And an option that you'll see in the menu in the upper left corner is Find a Club. And if you find a club, and what I did here, the screenshot is I went to find a club and I put in my zip code and hit search, and it came back and said, oh, you know, right across the bay from you in Delaware is the Lewis Amateur Radio Society, or right there in your own neighborhood, Cape May County. Cape May County Library meets at Cape May Courthouse. I've been to that library, and they have an amateur radio club. So I can go find those people and say, want to talk to my satellite? Chances are pretty good they're going to say yes. So this is a really great way to find ham clubs who will want to work with you. All right, then what do? Well, take this slide when you go talk to them. You find your ham operator or club through ARRL, and then you're going to use that commercial off-the-shelf software to find, this is complete alphabet soup here, software defined radio system, SDR, such as RTLSDR.com. That's one that we are testing. Serenity's call sign, the satellite call sign will be WU2M. That is Rocco's call sign. If you call that call sign now, you're going to get Rocco. But when Serenity is up, we're going to use that call sign to talk to Serenity. Serenity's public channel, as you've heard me say, is called Mode 2. And when I get into the command structure, we use the term M2 for that. The frequency range is 437.1. And as you saw on the timeline, it's going to be from about the first day that it launches until about 30 days after. So probably end of September to maybe the end of October. Communications are half duplex. So Serenity is very, very simple. It can listen, it can receive, it can transmit one at a time. So while it's receiving, it's not transmitting. While it's transmitting, it's not receiving. It will listen. It gets a call from you. It's going to transmit, and it's going to go back to listening. There's 3 commands you can send it, 3 commands available in public mode in M2. Status, list, and RAD, which stands for radiation. Okay, so here's how you put a command together when you want to talk to the satellite. It's like a phone call. So it's going to be the call sign you're trying to reach, your call sign at your station, the mode, you're in M2, you're in public mode, and then the command, one of those 3 commands. So it's just like I call you on the phone. Hi, Joe, it's Liz. Hi, Serenity, it's Liz. So WU2M, my call sign, M2, and then one of these 3 commands that you see bolded below, status, list, or RAD. If you ask for status, you're going to get back a lengthy response, and it's going to reverse the order. It's going to say, hi, Liz, this is Serenity, right? So it's going to be my call sign, WU2M, and then these terms. So I'm going to get an H for satellite health, and then 0 if there's a problem, or 1 if it's good. I'm going to get battery percentages on the 2 batteries, battery A, %, battery B, %. Solar panel voltage, S, and the voltage from 0 to 20. Latitude LT, plus or minus, longitude, ln, plus or minus, and then the date or time in the other order, time and then date. Hours, minutes, seconds, hundredths of seconds, year, month, day. That's status. If I ask for list, if I go WU2M, my call sign, M2 list, I'm going to get back a list of all the stations that have contacted Serenity in the past 7 days. So that's very cool for us. We want to know. We want to see you up there. We want to see hundreds of stations talking to Serenity. And you might want to know that too. You might want to talk to some of those stations and say, what are you guys doing? Maybe you find a partner to work with on something. RAD is going to give you back that list of dosimeter readings from the 2 dosimeters. One is wrapped, one is unwrapped. You can work with your students. The students usually understand that the wrapped one should see less radiation because it's got protection. It should be protected from radiation and not see as much radiation as the unwrapped sensor. Let's see what the readings actually are. And that's really fascinating. And I'm going to show you some pictures of some things you can do with that data. Okay, so this is the radiation experiment. And I realize that I'm running up on my 30 minutes already. So I'm going to urge you to take a closer look at this. It is available on our website. And you can also ask me for it. But it shows for the version that we have flown on the balloons and on Perlan and on Blue Origin, how we do this with an Arduino Uno and a couple of Geiger counters. What we're flying on Serenity, we're using Raspberry Pi because we've got so much going on, and we're using some smaller dosimeters, but this gives you a good understanding of how the experiment works. Okay, and then this is the type of data you get back. What you get back is comma-delimited string of data. So first thing you have to do is pop it into a spreadsheet, and you see a little image of that in the upper left corner. This is a typical spreadsheet once you have dropped that data in there. And then these are typical charts from various flights. And you can see in all of them, there's one that's seeing a lot more radiation. That's the unwrapped one, and one that sees less. That's the wrapped one. And you can do some great things with your students, asking them, what do you think are causing these spikes? Which one is which? You can even learn some things about flight profiles. You see some of these profiles are very flat. That is a long flight that's not changing very much. That would be a glider flight. One that goes up and comes down fast, that's going to be a balloon. Okay, so we are super, super excited to see what kinds of data we get back from Serenity in orbit. This is how you talk to us. This is us talking to some girls at a girls' event at a Challenger Center. We love working with students. We love working with teachers. And I want to know if you have questions. Here's my contact information. You can find us on our website. You can find our email on our website. It's info, I-N-F-O, @teachersinspace.com. And that's my cell phone.
There you go.
Hey, Liz.
Yeah.
Liz, it's Chris.
Hey,
Can
Chris.
you hear me?
Yes, I can.
Hey. Hey, I just wanted to add to the charts and telemetry data that a lot of that can be used to compare flights too. So like if you fly over the same region like we do with the balloons, you can compare data from one balloon to the next, or one flight to the next. So it's kind of an interesting aspect as well.
It totally is. That's Chris Murphy. It was his 11th grade student who came up with the idea for the Dual Geiger counter, and it's Chris who started and still runs our balloon program. Thank you, Chris.
Liz, this is Jim. Can you hear me?
I sure can. Go ahead, Jim.
Calvin asked a question. He had a couple of questions. He was wondering about the dimensions of the CubeSat. And I told him, he asked, are they the 10-10-10 standard frame? And I told him I thought they were. And he also was wondering about the mode of communications. And I believe it's voice mode. It's just regular, it's not APRS, it's nothing fancy, you're just transmitting these in voice mode.
Well, let me start with the first one. So the dimensions, yeah, on the 1U, it is a 10-10-10. If you can still see these slides, on the 3U, they're stacked on top of each other. So it's 30-10-10. And for talking to Serenity, it's not even voice mode. I think it's A25. Hashi, I know you're on the call. If you know, you can correct me. But it's like very basic back and forth. Thank you so much, everybody.
All right. Thank you.
Take care.
All right. Bye.
Bye.